Okay, all right, let's get started. So before continuing on with solar, a reminder, right? Midterm is next Monday. So May 3rd, and this will cover up to this Wednesday. Okay, so whatever we finish this Wednesday, we can cover on the midterm, which is next Monday. Is the day still good for everybody, May 3rd? Any additional conflicts? All right, okay, so still the same date. The difficulty of the questions on the midterm will be similar to the difficulty of the question on homework. Right, so again, it's a take-home day-long midterm, but I don't expect it will take you the whole day. The midterm is planned to have a length of around 2.5 hours, let's say. So do allocate sort of sufficient time for it. Yeah. A question? All right, okay.
Hi,
Yeah,
Professor. I have a question. So where do we submit our lab report?
Where do you submit the lab report? So did the TA not create a submission in Canvas?
I don't see any types for the lab submission.
All right, so that's okay. Then I will create one today.
Okay, thank you.
I'll create one today. All right. Thanks. Any other questions? All right. Okay. Good. So today, what we'll do is we'll finish up on solar. Right. So today, is we'll look at something called active solar. This is what's more common called solar PV. And what this means is basically a solar generation that creates a current. And so what we want to do is so the goal is really to do the following. As you take some solar cell, you have some solar cell, let's say, and then the goal is to eventually get this to look like a solar cell. We want to convert so this looks like a circuit model. We want to have an equivalent circuit model. So we want to turn the solar cell into something like, so it turn out to look something like this. Okay, so we'll somehow turn it into a current diode model. One of our goals. The second goal is to understand how a solar array works. So we'll look at solar array. So what happens if you stack, say, many cells together into an array? What happens to the voltage? What happens to a current? And we want to understand sort of how to control the current and voltage out of solar cell. Right? So that's our goal, to take a solar cell, which the way it generates electricity is actually quite non-trivial. It's a very non-trivial way of generating electricity. But we're going to have a basic understanding such that we can get it to look like a current source on the diode. Our goal is to get this to look like a current source like a diode. So if you look at a solar cell, right, active solar cell, then basically we're going to talk about silicon-based solar. Right? So our material for the solar cell will be silicon, be a semiconductor. There are other materials out there that are sort of much more advanced materials, but we are going to talk about silicon for now. Okay. So and we're going to think about a silicon crystal where you have many atoms arranged in a fairly sort of lattice structure. So silicon by itself is a pure silicon is a pretty good insulator, right? So the way we make semiconductors is we add impurities to it, and we can either dope it with phosphorus or boron. So this is already where you see the similarity with a diode, right? So the way you make the solar panel at a very basic level is similar to how you make a diode. As you dope silicon and you put two of these two materials, a p-type, n-type together, like this. So one of them, right, n-type has an extra electron, and the p-type has a sort of missing an electron. So this is, once we dope, this is what happens, right? So you have a electron, or this extra electron hanging around. This is called a hole or a space for electron. So the goal is, right, when you have these two materials together, to get the electrons to move, and thus creating a current. So, okay. So our goal is, now you put them together, you put the two together, and then we'll try to create a sort of possible path for current to come out of this. So the idea is really simple. You put an n-type on top. You have a p-type on the bottom, right? We create this kind of, you just sandwich this two, not sandwich, you stack this on top of each other. And then let's say you create a load in between, right? You create this load in between. Okay? Then what happens is you have photons, right? You have solar irradiation coming from here. So that's basically photons coming here. What happens is you encourage the electrons to move this way, right? The electrons since n-type has extra electrons hanging around, these electrons will try to, once you have photon, a photon comes in, some energy of the photon can knock out this electron, and then this electron moves around, and then you create this kind of path. You create this kind of path of the electrons circulating between the two types of materials. Right? So this is how you create current. Any questions? So which way does the current flow?
So
the electron
from the N and then to P and then back from P up to N, right? And then it keeps circulating again, right?
Yeah, this is your electron circulation, right? So electron circulates this way. So photon kicks it, gives some energy, then electrons move. Right, so which way does the current flow? As the electron moves in the way I draw, which way does the current flow?
Positive direction.
Right, flows in the other direction, right? So current is the positive charge flow. So this is current. Right, just keep this in mind. Right, so in physically, we want to talk about electrons, but in electric sense, right, for us, we want to talk about current flow. So it's in a different direction. That's fine. Right? So if you look at the photons, So for people who have some quantum mechanics knowledge, what we have is only photons of certain wavelengths can generate current. So if you think of the light coming out of the sun, you can think of this being a fairly broad spectrum, going all the way from, say, ultraviolet to visible to infrared, microwave, and so on. Only photons of certain wavelengths will generate current. Right? So why this? Anybody taken quantum?
I'm not really sure, but I think it's like there's those violet or like extra light give like most energy compared to the visible light and the lower.
Right. So the key thing to remember is not that the more energetic the photons are better, right? I think what Wenxuan is right is you have a certain band gap. So only photons of the right energy can excite electrons to kick them out. So what you have is you have electrons, right? So electrons you have in some state. This is the conducting, they'll become conducting if you kick them out, kick them high enough. Then you want basically photons of the right energy, right? So if the photons coming with energy that's too low, so too long a wavelength, then they pass through the material, nothing happens. If photons coming with too high energy, what happens is actually it heats up the entire material, but doesn't necessarily generate current because they're too energetic. The electrons, there's too much energy for electrons to actually jump to the right layer, to jump the right gap. Okay. So there's only some wavelengths that is correct, that can excite the electrons, and that depends on the material. Okay. So silicon, I think, is in the infrared or visible light range, right? So there's only a certain amount can work. So what this means is these are not 100%. Okay. Actually, efficiency is quite low. But anyways, they're not 100% efficient because if you remember of the solar energy we talked about from before, this 1.3 kilowatt per meter squared. That's a lot of power, but that's for over the entire spectrum, right? So if you have a solar PV, not all of that will be generating current. Actually, only a sort of narrow band gap. Therefore, you have a narrow wavelength that would generate this sunlight. So something to remember is you have an efficiency loss because we're fundamentally, the law that governs how materials work. Right? So a lot of researchers, how do you capture more of the light? How do you capture another wavelength? How do you do these things? So remember that all these things have efficiency, and there are some fundamental limit of the efficiency if you use certain kind of material. Okay, there's a fundamental limit to how efficient it can be. So there's no such thing as a panel that's 100% efficient or even close to 100% efficient. Right? Okay. So you have, so that's just something to remember. We won't go into any more of this detail about how exactly the equations governing this, but this is a picture to have in your mind. Right? Any questions about this? The process? Not entirely, no. There's two effects going on. So if you look, so I think Alex asked, what exactly is the effect here? There's actually two competing effects going on in this kind of panels. We won't cover both of them, but this has to do with the electric field that's in between the two materials and how exactly the electrons move between the two materials. So it's not that simple. So it's beyond the scope of this course, for sure. So if you're interested in that, then there are, I think, sort of solar or at least the quantum mechanics course you can take that'll go into a lot more about this. Right, so what I do here is you just have two materials, just put them together, but it's not, right? What happens in between is quite complicated. There's a field effect. There's electric field effect between the two materials. Okay, so any other questions on this? All right, so okay, so we get this picture, right? So you look into more detail as again, what we have is a PV cell is actually a diode. This PV cell. So when we convert this to the electric diagram, electric circuit, equivalent circuit, we'll see a diode. We'll see a diode. So this is actually not unlike a diode. what we have is sort of photons. Can excite the electrons, and they can and this sort of creates current. So you need some excitation process, this current. And then if you think about this diagram and the fact is a diode, then what we have is because PV cells are diodes, right? They're essentially built like a diodes, or like diodes. Only produce DC current. So it turns out there's sort of only one way that the current can flow. Right? There's only one way the current can flow, and because we have a PN junction. Right? We have a PN junction in this picture, so we'll see that this will behave like a diode. So the picture we have before going to the circuits and writing down a lot of equations, the circuit will be built up something of a current source. So what this current source comes from, this is the solar energy. Because of photons that can excite electrons, we have a current source. And then this circuit will also have a diode in it. This is because of PN junction. So thus we'll build a circuit out of these two components for a solar cell. Right? These are our two sort of basic components to build the circuit, to build an equivalent circuit. Right? Whereas the how much solar energy you have controls the amount of current you can generate, and how this current flows is defined by the fact that you have a diode in the you have a diode by the way you construct the material. Any questions? Something now? Okay, so let's look at what I drew as quite simple, right? It's just two things together. The way you actually make it is, of course, not that simple. You need, when you look at a solar panel, you see this sort of black, dark glass looking like thing. This is because what we have is you have a glass cover, you have a reflective coat, anti-reflective coating, you have wires, right, that carries current out, you have n-type, p-type, and a base. Right? So this is, if you look at a panel, there's sort of many layers sandwiched on top of each other, creates a solar panel that you see on top of roofs, for example. And cleaning this is actually very important. So often your solar panel loses efficiency is not because any electrical part, as you have to clean the solar panel. So there's a lot of maintenance issues going on with this. So this is one cell. This is sort of a single solar cell. That's how you make it. And the challenge with solar cell is, right, you cannot make them very high voltage or high current. You're limited by, you're limited by the material, and you're limited by, given a sort of a size of material, how much power it can generate. So if you look at your calculators, if you look at a calculator that has a cell, then a cell of a 4x4 inch cell will produce about 1 watt. So these are not terribly high power devices, right? But so if you have one cell, it provides a sometimes small amount of power, small amount of current. So what you typically do is you will stack cells together into modules or arrays. What you see on rooftops and in many applications as you stack them together. Right? You stack them together. So you stack them in a rectangular grid, with the goal of increasing the current and increasing the voltage rating. So each cell is quite small, and you stack them up to make a panel that has a much higher current and voltage rating. We'll wire them together like this. Is this clear? Any questions? So in what other device do you see this? So in solar, you definitely see a lot of stacking of cells. Can I think of another application where you stack many cells together? Batteries, right? So as Alex says, batteries, most battery packs are all small cells stacked together. So often for those applications, for each one of them, you have a fairly low voltage and current, and you stack many of them together to create sort of higher voltage and current ratings. And then you can stack the panels or modules in an array to even form a higher voltage and higher power system. So these are typical design criteria as you figure out how much each cell can provide. Then you figure out how many of these do you need to stack together to form an array. So you see this all over the place. Most time you'll see arrays stacked together as around rooftop of buildings, or here as a backup communication infrastructure for a cell tower, on top of parking lot, houses and all that, right? So you'll see there's quite a lot of them. And let's do an example to compute, depending how you stack, what kind of voltage and current you get. Okay. So let's say we have some, formation like this. We'll have a panel and array like this. And each of the cells provide a maximum power of 2.5 volts, so relatively small. And they are rated at 0.5 volts. So the voltage they can generate, the maximum voltage they can generate is 0.5 volt. And they can generate max power of 2.5 watts. So then each panel has 9 cells in series, 4 rows in parallel, and then we have 8 panels here. And we want to compute exactly how much power we can generate out of this entire array. Okay, so we want to compute the power and the power output of the array and the power output of the panel. Right, so we want to find, if you have one cell of this form, if you stack them together, how much power and voltage do you get? Right? So let's look at for a panel. Right? So for a panel, we have 9 cells in series. So what that means is you have all these cells, you connect them in series. You have 9 of them. So if you connect things in series, do you increase the voltage or do you increase the current?
Increase the voltage.
Increase the voltage, right? Things in series must have the same current. So this is where you increase the voltage. So when you stack them, basically the voltage just goes up linearly, 0.5 times 9, so altogether you get 4.5 volts, right? And then for the entire power of the panel, this just depends on how many cells you have. So this is just 2.5 times, you have 9 in series and the 4 in parallel. So 2.5 times 36, we get the whole thing is 90 watts. So this is the amount of power we have. Then total current is pretty easy to compute. Current is power over voltage, 90 over 4.5. This is 20 amps. Right? So this, if you view the entire panel as a big, big solar device, then it's rated at 20 amps and 4.5 volts. Okay, so that's how you treat each panel. Then you can stack. Yeah, go ahead.
Quick question.
Yeah.
For the 4.5, wouldn't that just be one series of the 9? Because there's 4 rows, right?
Yeah, so if you, okay, good question. So if you connect these, what happens to the voltage? Yeah, for those.
I see.
They have the same voltage, right? So things in parallel
Yeah.
has the same voltage, things in series have the same current. Right. So yeah, so you can compute the voltage for 9 of them. Right? Every column or everything series has a, every stack creates the same voltage. Right? And it's important for them to be at the same voltage actually. So when you have an array like this, you need them to actually be at the same voltage. Right, so these are the same voltage. And then you have a panel that draws 20 amps. So if you build an array out of this, it has 4 panels. Sorry, this has 2 columns of 4 series, 4 panels in series. Right, so this is nothing but you keep stacking this again, right? You treat each one of them as individual block, and you can keep stacking them. So the voltage of the array is the panel voltage times 4.5 for each of the array. Panel voltage times 4, 4.5 times 4, we have 18 volts. And then the total power for the array, this is, you have 8 of them, so we get 720 watts. And then the current is simply power over voltage. $40 amps. Okay, sorry. So this is what happens when you stack things. Any questions about this?
Professor, can I ask a question?
Yeah, go ahead.
So yeah, could you please scroll up a little bit? And yeah, so basically, where does a 2.5 from in the P panel?
Oh, watts, right? So each one of them produces 2.5 watts.
2.5 watts. I see. Thank you.
Yeah. Any other questions? Okay, so it's likely you'll get a question like this on the midterm. Okay, so this, where we stack array in various configurations. Okay, so this is typically a pretty easy question to do, but then you don't want to lose points, right? You don't want to lose easy points by mixing up series versus parallel or things like that. Okay. Okay, all right, so this is, right, so all the question goes like, you have some geometry, you stack things in a certain way, then you given a per cell parameters, you want to compute the array, array voltage, power, and current rating. That's very standard calculation to do. So this is,
So,
yeah, go ahead.
so the 18 volts is per series of panel, and then
Yeah.
those series are also in parallel, those two columns.
Right, yeah.
Okay, I see.
Yeah.
That's why the voltage is the same, and then you use
Yeah.
the power to divide by the voltage to find the current. I got it.
Yeah, yeah. So all the question goes like this. So what you may not see is you may see this being flipped around, right? So I can tell you the configuration. I can tell you the total power and the total current rating, and ask you to find the per cell parameters. That's one way to ask a question, right? So I can ask a question like that. So right, when you do homework questions, when you look at examples in class, try to think of different twists that can be done. Right, so that's most likely your midterm will not be asked a question exactly the same way as a homework question, just with the numbers changed. Right? Be sort of maybe a different way of asking a question. All right, so those are panel calculations. Again, pretty simple once you get the geometry correct. So another thing we often want to know for solar is how much energy do I get per day? Right? So last time we covered solar power density. Right? In this week's homework, also there are some questions about solar power density. But then the question is, we often want to know if this is the solar power density, this per time, then out of the whole day, how much energy am I getting? How much energy do I get? How much energy do I get if I have a sort of each time I have this kind of power density? So the total energy is you basically integrate over this Gaussian, right? You can integrate over this Gaussian. So instead of doing this integral exactly, what we'll do is we'll just integrate for you. We'll just integrate this for you. Basically, you can think of this integral being roughly equal to P max, the maximum power you can produce during the day, times a factor that's square root of pi times sigma. Okay, so this is what the integral comes out to be. Right. So if the question asks you what is the total energy you can generate, then you can use this energy equation. Right. If it asks you for the power at a particular time, you can use the power equation. So let's do an example to look at this. Right? So this is again pretty simple. If we set if our solar power density is given by this equation, and we know the maximum power during the day you can generate as 100 watts. Then we want the total energy. Okay, right. So with the energy we can get as a maximum power multiplied by this factor 2 pi sigma. Okay. So how do I compute sigma from this information? Which of these numbers has to do with sigma? The question doesn't directly give you what sigma is. So which of these parameters have to do with sigma?
Two sigma squared equals to 12.5. Is that
Right.
correct?
Yes. Right. So if you look at this equation up here, 2 sigma squared sits in the bottom. So here we have 2 sigma squared equals 12.5. The sigma you can compute to be 2.5. Then the total energy is easy, 100 times square 2 pi times 2.5. This is 627 watt hour. Any questions about this calculation?
Can you go up one slide? I want to see the formula. Okay, thank you.
All right. Any other questions? Okay, so this is sort of the bulk computation, right? So this doesn't necessarily have to do with how each solar cell is made. It just if you know this kind of parameters, you can compute the power from array or total energy generated by array. So if you put in your home, and again, since solar can only generate DC current, when you put a solar array in your home, you always need a converter that goes from DC to AC. Most loads in your home still requires AC current. Even if you have a computer that's at the end of the day runs on DC, but still the way it's constructed, it still needs AC current as the input. So when you put in your home, you put solar, you can charge your battery directly. You can charge your battery actually without conversion. But then for the rest of the load, you do need to do some conversion, right, to use your solar. Okay, so then if you don't have a battery, but you connect it to the utility, then you have a meter that's connected to the utility. Okay, right? So, and then of course, it's often useful to have a battery. It's often useful to have a battery together with your solar panel to balance out the uncertainties in solar or the variation in solar. Right? So you use solar, you charge and discharge the battery, then you have a firmer generation than compared to, say, if you don't have batteries. Right. So then if you have a battery, you set to charge and discharge, power the load. And then what you always need to do is you need a inverter. Right? You always need an inverter to convert DC to AC power. And often you need to synchronize that to the grid waveform. Right? You need to convert to 60 Hertz AC, and then you need to synchronize this AC waveform with the grid. Right? So if you're interfacing with the utility. So if you install solar on your roof, there's quite a bit of electronics and control circuit that goes, that's sort of in this converter, that you need this kind of circuitry to make it work with utility, to make it work with the battery. All right. So one thing to keep in mind, or one application to keep in mind, is if you look at this sort of standalone system, you have a DC going through a converter, then going through a load. So can you think of applications where this is not very efficient? Or you don't want to go through a conversion stage? So if you're talking about your home, then this loss is not very large. It's sort of small loss. But can you think of other applications where this loss may be large because of this conversion?
You mean from DC to AC?
Yeah, from DC to AC. Then start using the AC to power the load.
Not counting in the battery discharging and charging, right?
Sure, yeah, let's pretend, battery is its own stuff. But can you think of, where you would be inefficient or where you have large amount of loss if you do this kind of conversion? Right. So you see this kind of conversion loss or high losses, this what you would typically see is in data centers. So the way data centers works even right now is you have a battery. You need to charge a battery in your data center. So you need to convert whatever energy you have, either from the grid or from solar to DC. You charge your battery because that's your backup. Then you convert back to AC to go to your servers, computers. But at the end of the day, your computing service really needs DC. So you convert that AC to DC again to power your computing servers. So there's for many levels of conversion loss. Right? This is something so-called a double conversion loss in data centers. And this also can happen in electric vehicles. where you do this for many AC to DC, DC to AC conversions. And these losses can add up for this type of applications. So there are a lot of research on how to run a pure DC data center or how to run a electric vehicles with more DC power. So that's something to keep in mind. Right? So here, what we're drawing, it seems like, oh, there's just a converter, just make a DC AC conversion, then you can power the load. But if you look at a lot of applications where saving 5% of power is really important, then there are people thinking of ways to eliminate conversion stages or not going through so many conversions. Right? So for example, EVs or data center applications. Okay. Any other questions about this?
So wait, but that doesn't answer the question, why is converter like consume so much power loss like for that,
No, it's not that it's so much power loss. It's every time you convert energy, you will have some loss, right? It's not avoidable to have some loss when you do energy conversion. Then for your home, let's say you have a 2% inefficiency. That may make a few dollars of difference for your bill. You don't necessarily care, right? You won't swap out your entire architecture for saving a few dollars. But let's say if you're a 10 megawatt data center, that may very well add up to $100,000 a year, right? Then that makes sense, right? For you to take a lot of effort to save the number of converters you use. It's really that. It's really, does it make sense for you to spend a lot of effort changing the architecture? So for a single home, probably not. It doesn't make that much sense to avoid this DC to AC conversion. Whereas you're running a data center or you have an electric vehicle, you really want to extend the range of the vehicle, let's say by 40 miles, that makes sense to really think carefully about how many converters you need.
I see. Thank you.
Right. Okay, so let's keep going and let's look at the design. Right. Okay, so let's go back to our cell and look at what exactly does a cell look like. Right. So if you have a cell, you have some photons striking the material. Then what happens there? Well, so as a reminder, right? So our cell is really, if you just at a very sort of loose level, it's a PN junction. So it's a diode where P is anode pointing to the cathode, the N part of it. So we start off with a diode. And let's see what happens when you have a diode, right? When you have an ideal diode and a PN junction. Okay. So as a reminder, if we have a diode, we have the IV curve is, as the voltage increases, the current increases. As the voltage decreases, there will be some reverse saturation current. There'll be some reverse saturation current for this diode. Okay. So a solar panel is essentially a diode combined with a current source. But before talking about the current source, we need a better equation to model what this curve is. So we need some mathematical equation to fit this curve. And the mathematical equation we'll use to fit this curve is the exponential equation, is this exponential equation. So the equation we'll use is the current as a function of voltage, this I0 times e to the Vd over Vt minus 1. Right? This is the current equation we'll use. Okay, so if you look at this equation, it has sort of many parts to it. Right? So I list all the parts here. So what this model says, if we take a closer look, we can see is, so if you look at this behavior of this equation in different regimes, All right, so if you look at this regime, then if VD is very small, if this goes to minus infinity, or if this is much smaller than much smaller than 0, then the current is negative of I0, which gives you this reverse saturation curve, right? So we want to capture as if the voltage is very small and reversely biased, you have negative I0. This is your reverse saturation current happening here. Then if VD is large, then you have I is roughly this exponential growth, right? This is exponential growth, meaning as a diode, as you forward bias more and more, it's a very good conductor, right? Because a conductor. So this goes up very fast. Then if you look at, so when is current equal to 0? For what value is the current actually 0 in this model? So I go from minus I0 to exponential growth in current. When do I cross this, the point where I equals to 0? At what voltage?
Zero.
No. So right, yeah, so 0, sorry, yeah. So this is, we have VD equals to 0, that's correct. You have this I being 0, right, which makes sense. Okay. So this is the sort of empirical, or not empirical, but this is the curve we'll use. And there's a lot of constants in this curve, right? A lot of constants in this function. That's just comes because we have this thing called a thermal voltage, right? That depends on fundamental constant, and then the Boltzmann's constant, the temperature, and the elementary charge. So to derive this, again, we need, going to more quantum than we really want. So for us, sufficient just to remember this as the equation for the diode. This is the diode equation, and to know where to look up this constants. Okay. So for in a question, you often see in a questions, it's often assumed that you know where to look them up. So either remember the slide, right, for the values of Q, K, and absolute temperature, or be able to look them up online. Any questions about this equation? Okay, all right. So with this equation, we're basically almost there. Where the next step is to really write down the circuit model for a solar PV cell. So with before doing that, let's take our break. So we'll come back at 3:30, and we'll finish with this, and we'll write the equivalent circuit based on a diode and a current source. Right, so let's break until 3:30. And again, have any question about the homework, then you can ask now. All right, so let's get started again. Right, so this is continuing from the first half of the class. This is our diode model. We have exponential model for how voltage relates to current. Then if you look at the solar cell, so you look at the solar PV model, and then you try to draw where the diode is. What this becomes is, so let's draw from right to left. So this is our load. This is our load. This is our load. Well, our diode, right, points from P to N. So we have a PN junction. So we have a diode pointing this way. Then our solar cell the solar radiation excites the flow of current. So this is our current source. So we have this as now our model for our solar cell. We have a current source, IS, as created from solar. We have a diode sitting in between. Then we have a load current. Then we have this I. This is the load current on this side. Okay. So here we have the voltage across a diode. Any questions with this figure? We'll do a lot more calculations, but any questions with this figure right now? Okay, so this figure.
So the source is.
Yeah, go ahead.
So the source IS is the upper part, like compared to the model.
Is the upper part of.
Because when I look at the model, I know that the N-type, P-type materials is like acting as a diode, and then the load, and then.
So the source is right. So the source is the flow of the electron in the material. You can think of that way. You have a flow of electron in the material. So that's, and the reason it flows is because they're excited by the photons coming in. Right?
Okay.
So yeah, so you're pulling a current out of the load and you're pulling current out of the diode. And conservation of current has meaning that essentially you're balancing the electrons or currents inside the material. And we're going to think of that as a current source. Right? We're going to think of that as a current source. Okay. So we're thinking of that's the way that solar energy gets translated to electric energy. You can think of as you're creating a source of current inside the material. So this is our, yeah, go ahead.
Another question. So I'm just wondering why the electrons don't just go, all of them don't go directly from the end of the p-type, and why would they not skip the load?
Why would they not skip the load? Right, so there's a reason for that. So if you look at the N and p-type, so the question is, right, so there's a more basic question of that. As let's say you just stack two of them together, right? Why don't the electron just rebalance across the two? I mean, one has excess electron, one has, reduced number of electrons, one has excess number of holes. Why don't they just hop across and rebalance on their own? Right. So that, right. So obviously they don't do that. Otherwise you wouldn't have a diode left over. But the reason is between the two materials, you have a field that opposes the electrons from moving from one type of material to the other type. Right. So if you connect a wire, it's not that all the electrons will go, hop the gap, or they'll all go through the wire. It's actually, there's two ways for the electrons to go net. They can either try to hop across the gap between the two materials, or they can circulate through the load. And then the way we compute how much total current is generated is by adding up the current generated through each of the paths, right? One path, right, if you look at this, is the diode path, is the electrons going from N to P. Another path is electron going from the load. There's two ways for electrons to go. That's a good question. But the reason is they don't all go through one path through the diode is if you think about the diode, right? There is a voltage you have to overcome in the diode for the electrons to hop through. If you just put P on N type, the electrons doesn't equalize by their own. Right? There's no, the electron doesn't spontaneous flow from one type to the other type. This is because this voltage, you have this VT, right? You have this VT has to overcome this. Right? There's some voltage opposing the flow of electrons.
Okay, thank you.
Yeah. Other questions? These are good questions. Yeah. Any other questions about this?
Well, just curious, is the direction of VD inverted?
It's not inverted, so the direct, oh yeah, so did I draw, that's, yeah, so I drew the plus minus on inverted, yes, sorry. Yes, yeah. Thanks for that catch. Yeah, I choose this inverter. So I will turn it around later. Yeah, but for now, the voltage is positive at the P end of the diode, at the anode of the diode. Okay, yeah, thanks for that question. That actually leads to the next slide. As I really don't want to draw a diode upside down and the current going downwards, right? So what I want to do is I want to flip this voltage over. Okay, so the much more common way of drawing the solar cell is to flip the current source and the diode. So this is nothing changes except we flip the diode and flip the current source so that I can draw the voltage in the sort of, from top to bottom. So I want to draw, I really want to draw it this way. So this is how we will draw the circuit. This is how we'll draw the circuit. Yeah, that's a good question. Okay, so most commonly we'll see the circuit draw this way. It's because we really prefer to draw the voltage with the plus sign on top of the minus sign. Right, so here what we have is IS. This is called the solar current. So the S stands for solar. This is solar current. This depends on how much photons you have. Right? This depends on the solar radius. So this is a number that depends on nature, basically. ID, this is the forward current. Right, so there's two things going on within the panel. One is there's some total amount of current we can have. Then there is a current through the diode. Okay, so now we can do calculations, basically. Now we can do calculations from this, based on this circuit, right? Because IS is again given by nature. But VD or ID depends on the load, right? So VD, this is a load voltage. We're going to think of this as controllable, right? So IS is given by nature, we don't touch it. But then VD is the load, the voltage that appears across the load, which is something we can set, right? We get to control the load. Okay, so these are the three things that come together. But if you look at the PV characteristics of this, as what you really want is the following. If you're at the load, your power is given by V times I. The power of your load is VD times the current you have. The goal is try to understand how does the power depend on the value of VD. If I change VD, how much power do I draw out of this? How much power do I draw? So if you look at the PV characteristics, this is a diode. This is a solar current. So the diode depends on the voltage. The solar current does not depend on the voltage. The solar current doesn't care what the voltage is. So if you look at the current through the load, this is the load current. Then you can draw how load current changes respect to VD. Right? So as VD increases larger and larger, your load current drops because the diode is now pulling more current. So as your voltage increases, the diode start pulling more current, then that current doesn't go to your load. So you want to balance your voltage versus how much current you're drawing. Right? So there's a VI relationship you try to hit. And for example, you may try to hit a sweet spot, let's say somewhere here. So this is up to us to control. We get to control the voltage. Given a voltage, we can get some current. And then we try to adjust the voltage to get the current we want. Any questions before we go to the equations?
Can you explain about the graph more? The 3 graph.
Okay.
Yeah.
So this is a diode graph, right? We're okay with this diode graph.
Yes.
So the solar current doesn't change. That's a constant. So if you look at this current, then this is IS, a constant, minus the diode, right? So this is I0 e to the VD over VT minus 1. This is that graph. You plot this as a function of VD, you get this graph, the third graph. Okay?
Okay.
Yeah, this is the graph you get, right? So you basically, since we get to set VD, you want to set VD at a reasonable value, right? You don't want to, for example, you don't want to operate on here in this region, right? You don't want to, have negative VD on current, but you also don't want your VD to be very large and you're pulling negative current. Right? So you want to operate as a correct region for VD. Any other questions for these curves? Okay, then the rest is basically cracking through the equations. Right, so now we want to look at the power output. So power for the load is V times VD. So here we have I is IS minus ID, right? So solar current subtract the current that goes through the diode. And then V is the diode voltage. So the output power is the voltage times IS minus I0 e to the VD over VT minus 1. So this is the power we get. So we want, often the question will be, given the VD, what is the power we have? This is the power we have. But then often what we want to do is we want to optimize this power. We want to find the maximum power we can extract from the cell. Questions about this equation? Okay, so this equation is typed out again, right? This is an important equation to remember. Use this as a fundamental equation for us for how a solar PV works. So this is how the power, right? So power depends on the load voltage you set. Right? If you set a load voltage, you draw a certain amount of power governed by this equation. Any questions? Okay, so we can plot this curve, right? We can plot this curve. So once we plot this curve as, right, so we can plot VD, we can plot VD, and we can plot, for example, P, power we draw. So VD being 0, this is definitely 0. This starts at 0. But then as VD increases, this goes up to a certain extent, then drops down again. Then it drops down again. Okay, so what we have is we have something called a VMP. This stands for maximum power tracking or maximum power point, right? So there is some V where you can operate to extract the most power out of this cell. So this is you're limited by some P max you can pull out of the cell. All right. Okay, so then the rest is just going through some basic quantities that we have for circuits, right? We often care about the short circuit current, the open circuit voltage, the operating point at maximum power, right? We want to understand all this. So the short circuit current is really simple. is if you short the output, if you have nothing as output, then everything goes through the, right? So if you have a short as output, then nothing flows through the diode because there's no voltage drop across the diode. The voltage drop is 0. So the short circuit current is equal to the solar current, right? The amount of current you generate when you have no load, right? When you short the load, we have a wire. Then we can talk about open circuit voltage, right? So if you open the load, then what we have is all the current has to go through the diode. Okay? So diode carries all the current. And here I have the total current through the diode as a current generated by the solar current. This is equal to I0 e to the open circuit voltage over VT minus 1. We can invert this and we get the open circuit voltage is VT times the natural log of IS over I0 plus 1. So these are sometimes the quantities we care about.
Can you go up one slide?
Sure.
Yeah, for this one, you said the voltage for both of them is 0.
The voltage across the diode is 0. This is a wire, right? So this is,
that's a
we're
wire.
shorting the output, so there's no voltage drop across the diode. So there's
Okay.
no current through the diode. There's 0 current through the diode.
Okay, gotcha.
Right. So we really care with, a lot of times we care about these things as these are the things we can measure. Right. We can measure the short circuit current, we can measure the open circuit voltage. Right? So these are the things we can measure. So we want to know how they relate to more internal quantities like solar current. Right? So solar current is something happening inside the material. We don't necessarily get to measure that. So one way to measure solar current is you measure the short current, the short circuit current. So solar current is again the representation, our circuit representation. Really, so if you want to estimate what that is, you can do it through the short circuit. Right. So let's do one example. That's pretty typical of the solar. So here we say we have ideal solar cell. Right? Meaning when there's no loss in the diode, there's no loss in the circuits. That has a reverse saturation current of 1 nanoamps, and this operating at 30 degrees Celsius. We know the solar current is 1 amp. When the compute output voltage, output power of the PV cell, when the load draws 0.5 amps. So we're given some information. We want to compute the output voltage and output power. So here is, we know IS, we know what this is. We know how much this load is drawing. Right? We know this thing is drawing 0.5 amps. We know this is outputting 1 amp. I want to know what's the voltage across this load. I want to know how much power this load is outputting. Right. So for these type of questions, so if you look at the equation, some equation say like this, right? This is our power equation. For this type of questions, it's always the case that you compute this VT, this thermal voltage quantity, because this quantity shows up in all the, this quantity shows up in a lot of the equations. So you may just well compute this first and get it out of the way. So this is Boltzmann's constant times the temperature divided by the charge on an electron. So the only thing that, that's a little bit tricky about this is you want to use the absolute temperature in kelvins. So it's important to not use 30, but use the temperature in kelvins. And then the rest are just fundamental constant you can copy and plug into this thing, right? And here we got 26.11 times 10 to the minus 3 volts. Okay. Any questions about this? All right, so this is our thermal voltage. Once you have the thermal voltage, we have to compute the voltage of the load. Right? We'll compute the voltage of the load. So there's several ways we can do this. One equation we can use is the current is equal to the solar current minus the current through the diode. So we know the current draw is 0.5. We know the solar current is 1. We know the reverse saturation current. So this 1 nanoamps, this is I0. There's 1 nanoamps. E to the V, we don't know, but we know VT. This is 26.11 times 10 to the minus 3 minus 1. Okay, so we can solve for V. You can actually explicitly solve for V here. You don't need to graph this. V is the natural log of 1 minus 0.5 times 10 to the minus 9, 10 to the 9, plus 1 times the thermal voltage, you get 0.523 volts. So you can solve this equation many ways. Then the power draw is voltage times current, 0.2615 watts. Any question about this calculation?
Can you go up one slide? I just want to see the problem. So this, you calculate the voltage across the diode, right?
Yeah, or the voltage across a load. It's the same voltage.
Oh, okay.
Same voltage. They're in parallel to each other. Any other questions about this? Okay, so for this type of calculation, it's not hard, but there's a lot of constants floating around. Right? There's a lot of logs or a lot of exponentials. So sometimes you're multiplying or dividing by relatively large numbers. So if you do this in the exam, especially, it's important to show your steps. So it's not uncommon to make a mistake. So if you multiply by things in the order of 10 to the 9, then it's pretty easy for your answer to be off by quite a bit, right? If you made a numerical mistake somewhere. So during exams, you want to show your work. Right? If you show your work and then the final answer comes out differently, you don't get, you lose maybe 1 point, right? But then if you don't show your work, if you just write down the equation in the slide, and then the numerical answer appears, if it's wrong, then it's wrong. There's not much I can do about it, right? So it's important to show this kind of steps. Okay, show how you're finding V. Okay, so it's quite common in exams for the answer to be off by order of magnitude, right? Just because you have things like 10 to the 9, you have to deal with. So remember to show your steps, right? Just because you can't use computers, doesn't mean that every question the answer is you write down the equation and then a number appears. Right? So if it's that way, then the answer is wrong. Then not much I can do about partial place. Okay. Right, so this kind of question, just do it carefully, do the log carefully, right? Do the division, do it carefully, and then look for you get some answer that's reasonable. Right? So the voltage should come out to be around not too different than 1 volt, and the power should not be some very large or very small number. Right. So any other questions about this? Okay, so this is a standard question. I'm drawing 0.5 amps. How much power do I get? But often as I want more power, right? The goal is I want to extract the maximum power possible from this. So the next question captures this. It's saying I have a solar cell that we use with a reverse saturation current of 1 nanoamps operating at 20 degrees Celsius. The solar current is 0.8 amps. I want now to maximize the power I can draw. So I want to compute the voltage and the current such that I can draw the maximum amount of power. So for this question, as IS is given, this is 0.8 amps. But then the rest we don't know, right? We're going to optimize over this voltage such that I can maximize the power draw at the load. So how do I do this? How do I maximize the power? As engineers, this is most times what we care about is the maximum power draw. Right, so you take a derivative, right? So you take a derivative, set it to 0, and try to find what that is, right? So we have power as voltage times current. So what I want is I want to maximum power draw means that I want the derivative of respect to voltage to be 0, right? So we want to solve this to find the voltage that solves this equation. So when we do the derivative, right? So let's do this derivative. This is use the product rule. Right? This is the current plus V times di dV, where I is Is minus I0 e to the V over Vt minus 1. So if you look at this equation, di dV, you take I0 over Vt e to the V over Vt. So then at maximum power, what we have is we want to set this derivative to 0. So we have 0 equals to dV. This is Is minus I0 e to the V Vt minus 1 plus V times. We want to get this thing to be 0. Okay, we want to solve this equation to get to be 0. Right, any questions up until now?
Question about the derivative of power over voltage.
Okay.
That's equal to I plus voltage derivative of IV. Where did you get that formula from?
That's the product rule, right? That's the product rule of derivatives. So if you have fx times g of x, this is f prime of x, g of x, plus f of x, g prime of x. It's just the product rule of derivatives. So derivative of v is 1, right? Then v times derivative of I respectively.
I thought you just taking like partial derivative of the I, of the v, and then just eliminate the I. My bad.
No, but I depends on v though, right? I is a function of v.
Yeah, makes sense.
So otherwise it's not a meaningful derivative, right? So the whole point is I depends on v, right? So that's the important thing to remember. Okay, all this equation, I depends on v. You know, this is the current depends on the voltage. That's how we solve this, this kind of equation. Okay, so we can take this derivative. So now again, there are two options here. You can either just graph this. Right? So we are, again, you have access to your computer during exams. You want to just graph this and figure out what V is. Right? So you can graph it. Now, if you want to make things slightly simpler, you can collect terms. So this, if you collect terms, this is Is plus I0 minus 1 plus V over Vt I0 E V over VT. This is, if you collect terms, you have this equation. Then we can keep going, right? We can move it. So we have this whole thing equal to 0. Then if you do a little bit more work, we have 1 plus V over VT e to the V over VT. This is equal to IS plus I0 or IS or I0. So now we know IS, we know I0, we know VT. Right? So plug all of them in. You can again either graph this, use your computer, or however you want to solve this. You get V that's at the maximum max power, V maximum power. This is 0.85 millivolts. Okay, so if you want the maximum power to get out from your cell, then this is the voltage you should set the load to be. Right? So again, you can do this because after the panel, you have again power electronics. You have electronics. We can set the voltage. We can convert the voltage to another voltage if we want. So this is really up to us to set what the voltage we want to be. So for this question, for the maximum power, we want to set to be this voltage. Then the current, you just plug this into it. -1. Then plugging all the numbers, you have 0.757 amps. So the maximum power as the voltage times current. 95 milliwatts. So out of this cell, you can get this much power to come out. Okay, so this is where you want it, this is where you want to set the voltage and current to draw the maximum amount of power. Any questions about this? Okay, so you're expected to be able to solve an equation like this, basically. You're expected to be able to, let's say, graph this in MATLAB and to be able to solve it, or just get a computer, try many values of V and see which one gets you closest to there. Okay. So again, to be clear, is we get to control the operating point, right? So we have a load. We get to control how much power we draw from the cell up to the maximum. So there's different operating point we can hit. So again, if you look at the VI curve of the cell, it looks something like this. Then by changing different loads, I can hit different points, right? So if my load is a resistance, and I have some resistance, I can hit a point on the VI curve. If I change my resistance, I can hit, for example, another point on the VI curve. So we have, this is a source. This is the power source. The way we draw power from it is by controlling the voltage of the load, or equivalently controlling the resistance of the load. All right, so then from the previous example, we want to put this in terms of voltage. Then we have the maximum power tracking voltage as 403 millivolts. Maximum power current is 0.757 amps. Then the resistance, right, you should have to get the maximum amount of power is around 0.59 ohms. So we have the ability to control all of this. Any other questions about this? Okay, so let's do one final example for this class, right? So again, there's not that much more about this equations. It's just all the different ways you can use them. So one of the last ways you can use them is here we're not told the current or the voltage drives the load, but we're told that we connect the cell to a resistive load. And let's see what the power we have is. So here we have a resistor instead of the, so we know this is 10 ohms. We know the solar current is 1 amp. We know the temperature we're operating at. So we want to compute the power draw from the load or the power output of the cell. All right, so the way we do this is, again, we compute VT first. It's almost always you want to compute the thermal voltage VT. Right, so you plug in all the constants, you get 61 times 10 to the minus 3 volts. Then what we know is we know the current, right? This current, this is equal to both the solar current minus the diode current, also equal to the voltage divided by the resistance. Right, so this is our equation. And then we need to solve for V. Okay. So here we have V equals to IS times R minus R times I0 e to the V over VT minus 1. We have V equals to 10 minus 10 point minus 8 e to the V over 0.0261 minus 1. And this is our equation. Again, you can solve this in many ways. More easiest if you're using a computer, just do exhaustive search. Just search over V to find out what this is. So we get V is roughly 0.47 volts. And then the power draw is V squared over R. This is 10. And we get 22.3 milliwatts. Any questions about this example? Okay, so all these questions is the same equation. There's not that many equations for solar. They're basically one equation for solar, the current equation. Right? Then it's a different way of asking, the low power, low voltage, low current, and things like that. All right, okay, so there's no questions, and let's stop here today. The next time we'll finish with solar. There's not that much material left in solar. We'll finish that. We'll look at sometimes, what happens when things are not ideal. And then after solar, we'll go on to wind power generation. Okay.
Quick last question.
Sure.
So for the V value in this case, when we setting up the equation this way, and we can solve it by hand, right, during the exam?
If you want to, sure, yeah, you can solve it by hand.
Because I think I'm not really good with grafting on the computer.
Right, so that may be something to get good at in some way, because again, I'm assuming you have access to at least a graphing calculator. So the way to solve this is here you can iteratively solve for V. For this question, is you can iteratively solve for V. Right, as you can guess, V equals to 1 and iterate through these equations, you get it pretty quickly.
Okay.
Yeah. But otherwise, I suggest figuring out, right? So solving this nonlinear equation is not that hard. What you can do is you can say, okay, I have a V, right? Let me, exhaustively search between V between 0 and 2. Right, so let me just go through all of them with a difference of, let's say, 0.01, and look at which one satisfies the equation the best. So it takes a few lines of coding to figure that out.
So basically, like setting y is equal to 1, and then let them guess which value is gonna make both sides equal to 1.
No. What I mean is, right, so one way to solve this is, right, so here you're solving for V, right? We're solving for this voltage V. So there's two ways to do it. One is you can graph the right-hand side, right? You can graph what the right-hand side looks like, and then look at where you cross this. Another way is you can just try many different values of V and see which one minimizes the difference between two sides of the equation.
Okay, gotcha.
Yeah, so, but I suggest figuring out how to do that. This will be on the exam. Like some question like this will be on the midterm.
Okay, thank you. Have a nice day, Professor.
Yeah, any other questions? Questions about the homework?
Yeah, I had a question about the lab actually.
Okay.
Do we meet up this week to work on the previous lab, or how does it work?
Have you done your lab last week?
Yeah. Mhm.
There should be no meeting this week.
No meeting. Okay. Got
Yeah,
it.
no meeting this week. Yeah, it's
All right,
bi-weekly. Yeah.
Cool.